From last time we were talking about a domain in 2 dimensions and bringing this onto a 3-dimensional surface. So I want to introduce new for today a notation that they use, and I don't really like to use R because I'm used to using R as the name for a parameterized curve, but this is what they use, so I'll go ahead and use R as well. I was going to use S, but I don't know if that's going to be too confusing. What do you guys think? R's okay. R's okay. So in the past we've had R of t with one parameter t, and when we see one parameter t, then we can assume that this is a curve either in 2 dimensions or 3 dimensions. But when we have 2 variables like this, u and v, then I'm essentially looking at 2 parameters. And so what happens there is that this is going to have to live in 3 dimensions, otherwise it's some sort of transformation from R2 to R2. So to put it in 3 dimensions notationally, this is generally what we put. We have an x value in the I direction, not value, but a function, a y function of 2 variables in the j, and then a z function in the k direction. So I have these 3 functions, x, y, and z, that are like the x and the y and the z components of your vector. And this draws out a surface. And in the examples that we've had, we've dealt with square or rectangular regions. So I put the square bracket A to B just as an example. AB by CD or something for your domain. But generally speaking, this could be any shaped domain that we have. So graphically, we have some domain here, D, in the UV plane. And remember, this could be R theta, phi theta, were a couple of examples that we have, or we could just be plain regular XY. So if we look at a particular segment, like a delta U, delta V segment from here, we can define ourselves a vector delta U, and then another vector delta V, and then we have these vectors popping up here as well. So the surface itself, I think I drew the surface in green last time. The surface itself is curved, but we're going to be approximating with planes. And so the 2 vectors that we have here I think I went as far as drawing these vectors, but I didn't really do much with it. Let's So this is kind of like where we left off last time. And so what I want to do now is label these vectors and say what they are, and then do something with it to get the area of this little subplane, and then, you know, the integral will do the rest for us. So what we have here is this first one, this blue vector that comes from the delta u, is going to be the derivative of r. Now, this is now a function of two variables, right? It's a function of u and v. So I started to do a straight d there, but really it should be the partial of r with respect to u. And this is a vector, so we have to acknowledge that this is a vector. And then depending on the length of u, there's going to be some delta u business involved there. And then likewise, we have this vector over here, which is the partial of r with respect to v, with the delta v component. And so to get this area, which is what we're kind of looking for, we're looking for the surface area. To get this area of this plane, will give us our approximation, and then we'll just add it up by putting it into an integral. But to get this area, what do we need to do to these two vectors? You remember? Multiply how? There's a dot product or a cross product. So we cross them, right? But if we cross these two vectors, we know that there's going to be our result is a vector. So we take the magnitude of that. So the magnitude of the cross product is the area. So the area of this thing, let's call it ij. Area sub ij is equal to the cross product of dr, dv, or du. I guess it doesn't matter. Because it doesn't matter which direction we're crossing. Normally it would, because it's anti-commutative, right? Depending on how you cross it, you'll get the negative of each other. But if you're going to take the magnitude, it's not going to matter. Okay, so delta u and delta v can be seen as scalars, and the actual vector is just the dr, du, dr, dv. So we could take the delta u, delta v's outside of this magnitude, and so that just becomes the differential. So the total area then is going to be basically the double integral over the region D, and this is the original region that we're looking at, of the cross product of the derivatives with respect to the two variables, u and v in this case, or it could be r and theta, or it could be x and y, it could be phi and theta. And then I could just have put dA there, but we just put du, dv, and dv, du in whatever order is necessary. So this is your surface integral. This is your surface area. Okay. All right. We could do an example, I suppose. Do we know the surface area of a sphere? How about the surface area of a rectangle? If we just do a rectangle, it'd be easy. Actually, I don't know if that'll be easy. Do you guys want to do an example? 4 pi r squared. Let's find the surface area of a sphere. So let's use a sphere for an example, and let's parameterize it, give it limits, and then set up our integral. So there's several ways to parameterize it, and since this is in fact a sphere, probably spherical coordinates parameterization would probably be the best way. So the spherical coordinate parameterization uses phi and theta. So I'll use those two as my variables or parameters. And sphere radius r, let's use capital R. Let's say sphere. Should we use R, or do you guys want to use an actual number? It doesn't matter. We use R. I'll use capital R for a constant. There's too many R's here, that's why I kind of was wondering. Anyways, the parameterization is going to be with a constant R as your radius, that's essentially your rho. Your rho is going to be fixed constant at capital R. So R, and then I think it's sine phi cosine theta, R, capital R again, sine phi sine theta, and then rho, or in this case R, cosine phi. So this is your parameterization. And we should note that your phi and theta limits, I guess this should be an ordered pair. Your phi goes from 0 to pi if we're looking at the whole sphere, and then your theta goes from 0 to 2 pi. I suppose I could have just written this with inequalities like I normally do, but we'll get to that when we begin looking at the integral. All right, so we need a couple of things. We need the partials with respect to phi and with respect to theta, and then we need to cross them. So I'm going to start using a different notation for the partial of r with respect to phi, and remember the subscript notation to mean that you're taking the derivative with respect to whatever that subscript is. So this is going to be a function still, or a vector, a 3 vector. So r is a constant with respect to phi. Derivative of sine phi is cosine phi, and theta is a constant. Derivative of sine phi again is cosine phi. And then the derivative of cosine phi with respect to phi is negative sine phi. So I'm going to write it on top of each other because I'm going to eventually cross them, so it'll get me kind of ready to cross them. With respect to theta, cosine theta first, the derivative of cosine is negative sine, so I'm going to have a negative sine phi sine theta. Derivative of sine is positive cosine, so that's just r sine phi cosine theta. And then the derivative of r sine phi with respect to theta, since there's no thetas in there, it's all constant, so the derivative is going to be 0. So in this particular case, it doesn't matter what we cross first, because we're going to take the absolute value anyways. So we'll do the cross product, and we'll cross out the first row, first column, and then find the middle part over here. If you imagine I, j, k up on top here. So this is going to be in the I direction is going to be 0 minus a negative. I have an r squared sine phi squared cosine theta. That's my I direction. In my j direction is going to be negative. I imagine crossing out my middle column. I'm going to have 0 minus and a negative is a positive. R squared sine squared phi sine theta. And then in my k component is, this is going to be a little bit longer, but this is one that's going to be simplified. We got r squared, sine phi, cosine phi, cosine squared, theta. So that's the first one. And then negative and a negative is a positive. We get r squared, sine and cosine, so sine phi, cosine phi, and then sine squared. Theta. So that simplifies a little bit. If you get the r squared sine cosine phi, r squared sine phi cosine phi, and then you would have a cosine squared theta plus sine squared theta, which is equal to 1. So that simplifies that a little bit. All right. Before we move on, we're going to take the magnitude of this instead of just blindly take the magnitude. Let's take anything out that we can take out. So let's see, I think I need to change things that need to be positive so they look like they're all going to be positive. It looked like I could take out an r squared. There's a sine, almost. There's a sine here. And the sine squared and then a sine, so I can't take out a whole thing. So I could take out a sine theta, or sine phi, sorry. So what do we have left? I have a sine phi, cosine theta, sine phi, sine theta, cosine phi. Okay. Are you having fun with your trig? So now let's take the magnitude. This is going to be the magnitude of this thing squared. So you just take the absolute values of a scalar. So they're all, and assuming that phi is positive the whole way, phi goes from 0 to pi, and sine of phi from 0 to pi is always positive, so we don't need to worry about the absolute value there. This stuff, you square it, and when you do this business, you'll see a bunch of things follow the identity. You got sine squared phi, cosine theta, cosine squared theta, plus sine squared phi, sine squared theta, plus cosine squared phi. So from the first two, if you factor out a sine squared phi, you're going to get sine squared phi times 1, and then you have sine squared phi times plus cosine squared phi. That's just going to be 1 also. So all this thing disappears, and you just got r squared sine phi. So you can do the math or do the trig. That you'll see that this is going to add up to 1 carefully if you want, but just trust me that it's going to be that. Okay. So now we take this and put it into our integral according to our surface area integral. We have an integral of over D, our domain, of the magnitude of the cross product du and dv, or whatever the variables are you're working with. So it turns out that when we do this, and this shouldn't be a surprise, or should look very familiar to your triple integral spherical coordinate transformation, rho squared sine phi. This actually came out when we did the cross product, which is kind of like should be kind of natural to happen. Although it's not exactly spherical coordinates, because spherical coordinates is a three-dimensional solid. Remember that we're only working with a surface here. So our integral would be, depending on what we're going to integrate with respect with first, if we integrate with respect to phi first, the inner integral is going to be from 0 to pi, and then the outer integral is from 0 to 2 pi, based on your limits. But let's say that the antiderivative, or no, the cross product, the magnitude of the cross product is r squared sine phi, and our d phi goes from 0 to pi, and our d theta goes from 0 to 2 pi. So we're essentially integrating sine phi, r is a constant, and then integral with respect to theta from 0 to 2 pi is just that. So let's see, if we lay it all out, r squared is constant, you're integrating from 0 to 2 pi d theta, integrating from 0 to pi of sine phi d phi, then you have r squared times 2 pi, and sine from 0 to pi, did you know that was equal to 2? It's equal to 2. You do that, that's negative cosine, and then you integrate from 0 to pi, you put in 0 and pi, and you'll get 2. So, oh, I forgot the squared. So that's 4 pi r squared, which is what Alex said the surface area was, right? So, okay, good. That worked out. Peachy. Now, there's probably a way to get away from doing all the trig, since we already know we're kind of using spherical coordinates. We already know that that's going to happen, but I'll maybe tell you later. Okay? Questions? Surface area. All right. Now let's extend our idea of this integral just like we extended from the arc length. So I'll start off by saying recall the arc length. And back then, when we first started talking about the arc length, we came up with a parameterization. So let's start off by this. Let C be parameterized by R of t from A to B. So that's some curve. I don't care if we're in 2 dimensions or 3 dimensions. It's a curve that we can find the arc length of. And if you remember, the arc length is equal to an integral from A to B of the magnitude of r prime of t dt. You remember that? You remember that?
Yeah.
Yeah.
Sure.
So let's do a kind of like an analog to what we just did. So let S be parameterized by R of uv over some domain D. So now we have a parameterized surface of sorts, and then the surface area is equal to this double integral over D of the magnitude of not the derivative, right, but actually the cross product of 2 derivatives, since we have to deal with 2 derivatives here. So this is R sub u cross R sub v du dv. All right? Now, at some point back in the beginning of this chapter, this arc length became something else. We introduced a new notation for the magnitude of r prime dt. Do you remember what that notation was? Do you remember what this became? We made this length here, we made this into an integral over the curve C d little s. I think they call it S. Maybe they call it R. I don't know what they call it in the book. Do you understand that this notation here is the same thing as this notation here? So that's kind of like what we did. We're integrating over the arc length. We're integrating over the length of this curve, and so if we have nothing here, then all we have is just the magnitude of r prime, which is the arc length. And then we took it a step farther, and this is where we introduced the first thing that I talked about, at least in chapter 16, is called the path integral. So we have the path integral, where we have a function that we're integrating over the arc length. So now we're throwing in, instead of just having nothing here, we're throwing in an f function in here. So now we're integrating a function over the arc length. And this is what we know of as a path integral. So what I want to do is I want to build on our surface area and do the same thing. And I'm just going to follow the same sort of notation here and then integrate over that. And let's try to see where the notation changes a little bit. So what I want to say is that coming from the surface area formula, we can actually extend this to the surface area is equal to a double integral over, now I'm going to use capital S to represent a surface area. I'm integrating over a surface area. And so over here, I want to use surface S, where S is the actual surface that we're looking for. And then I have what's called, now remember this SA just stands for surface area. This is a formula for the surface area. This is an actual formal integral now called a surface integral. And the surface integral is going to be essentially a double integral over a surface. And when we say it's over a surface, that means we have to somehow parameterize that surface, just like we somehow have to parameterize this curve. This is a double integral over a surface of some function, and we're assuming the function is a function of x, y, and z, ds, where s is the surface area element. And to get us to work with that surface area element, we need to change it into this parameterization cross product business. It's getting deep, huh? Or it's getting hard? It's getting hard. So how could this happen? How could this be applied to something real life? let's say you're trying to make a steel marble. No, it has to be hollow. It has to be just the surface. So let's say you're trying to make a steel sphere, a ball that's hollow in the middle. So it's just, you're just looking at the surface. But when you're making it, you have a mold, right? And you're putting this alloy steel on this mold. And so what happens is that when you pour the mold, the heavier metals tend to go down in the bottom further down than it would be on top. Are you picturing this? All right, let's see if we can make up a problem. So let's, for example, let delta of x, y, and z equal to, and just one minus x squared minus y squared minus z squared be the density of a surface being created. So we have a density function and we need a surface. So let's make should we do the bottom half of the sphere, or should we actually do like a paraboloid or something? Let's do a paraboloid. Surface being created where S, the surface, is the paraboloid and let's say the paraboloid is Z is equal to, and let's go down the x-axis, so x squared plus y squared minus 1 below the xy plane. Okay, so we have a surface established and we have a density function that we want to apply to the surface to find the mass. Find the mass. Does this problem make sense? Okay. All right, well, let's see if it works out for us. What we want to do now is to find the mass. The mass is going to essentially be a surface integral over the surface S of the density function as a function of x, y, and z, and then ds, because we're not talking about a two-dimensional domain, we're talking about a two-dimensional surface. So it is important that this is not dA, where A is a flat area over a flat region. We're talking about S as a surface that's in a three-dimensional space. So what do we need to do? We need to parameterize S. Now we can do it one of two ways. We can assume our graph parameterization, that seems to be the simplest, or we can jump into something like a cylindrical coordinate system to maybe make it look nicer. But there's give and takes between the two of them. So let me write down both of them and we'll decide which one to use. So remember, there's an infinite number of ways to parameterize anything. So let's go with two parameterizations here. We'll go with a graph parameterization that I called. I think I called it graph, or maybe I think the book calls it a function parameterization, where your R is a function of x and y. It's natural to just use the x and the y because X and Y are being used. So X is X, Y is Y. Remember, yesterday we kind of used U and V there just so we can graph it, but I said you can use X's and Y's if you want. So X and Y, and then the Z, this is actual surface. So the Z is X squared plus Y squared minus 1. So this is your parameterization, the function of X and Y now. And then we need the domain. So the X and Y domain has to be, this is a parab. Did you guys get the picture of this, by the way? This is a paraboloid that's below the x-axis. So the shadow of this thing should be a circle, right? Circle of radius 1. So if I were to do this, I would integrate like this, and then it would look like then I would probably have to change it to polar coordinates because of the domain. The other way to do this is to jump straight into polar coordinates or cylindrical. And when we go into polar cylindrical coordinates, we're using r and theta now for our parameters. And we got x is equal to r cosine theta, y is equal to r sine theta, and then z is equal to z, and z is equal to x squared plus y squared minus 1. So translate that into polar coordinates, you get r squared minus 1. So if you, the nice thing about this is that our domain, if you do it this way, is just going to be the shadow that this thing is going to have on the xy plane, which is a circle. So r basically goes from 0 to 1, and theta goes from 0 to 2 pi. So these are two parameterizations. We can use the graph parameterization and then change it into polar coordinates when we do the integral, or we can do cylindrical coordinates from the get-go and then work it out from there. I want to talk about the graph parameterization because there's something special about this graph parameterization that, that comes up. So let's do this one. Which means we need to take the derivative and cross them, right? Let's take the derivative and cross them. And then once we do that, we're going to set up our integral. And then when we set up our integral, we'll see, that's when we'll see that we're going to transfer it into polar. But let's take a look at this and cross it and find a derivative. So r sub x, the derivative of the parameterization with respect to x. So derivative of x is 1, derivative of y is 0. Nice, right? From the beginning. And now the derivative of this is just whatever it is, 2x. So now let's take the derivative of the parameterization with respect to y. 0, 1, and then derivative of this is 2y. Okay, let's stop and pause for a minute. Does this look familiar? I've seen crap like this all over already. And I'm trying to get your mind to direct your mind into a particular point in time in class. There's gradients involved here. Right? Okay. Keep that in mind. Let's cross it. R sub x by R sub y. Oh, should have crossed it the other way. Anyways, let's cross it this way. Cross out the first column. I have 0 minus 2x. Cross out the middle term. The middle term has a negative built in. I have negative sign, and I have 2y minus 0. And then if I cross out that last column, I have 1 minus 0, 1. Had I crossed it the other way, I would have gotten 2x, 2y, and negative 1. Remember that negative 1? But as it is, I crossed it this way. I have negative the partial of f as a graph function, negative partial of y as a graph function, and then positive 1. But it doesn't matter which way we cross it because we're going to take the magnitude anyways. So the magnitude is going to be the square root of, I guess we have to square this, 4x squared plus 4y squared plus 1. So this is going to be your surface component, your surface area component that's going to go into your integral. So given that our d, let's make sure we remember that our d is equal to this unit circle. For now, let's just call it d because I'm not going to bother with a square root of 1 minus x squared business because I'm just going to change this to polar after I set it up initially. So the mass is going to be a double integral. I'm going to go from a surface integral to a double integral. Now, surface integral looks like a double integral, but technically it's not a double integral because I'm integrating over a surface. A double integral, you're integrating over a flat two-dimensional region. A surface integral, you're integrating over a surface. That's a two-dimensional region, but it lives in 3D. So try to see if you can understand the difference. So now this is going to be a double integral. My limits of integration will depend on this D region, a flat two-dimensional region. My density function comes next. What was my density function? 1 minus x squared minus y squared minus z squared. And then now my ds is going to be the dx dy along with this surface area element. So I could put dA there if I want, because I'm not quite ready with the limits yet of integration. But I'll just keep it as dx dy to say this is dx dy or dy dx in any order. That would be good. Okay? You with me so far? Kind of. Yeah. I got a couple of nods. Everybody else is just kind of. All right, so if I want to do this integral, which I don't, but if I want to do this integral, I probably would want to change it into polar coordinates. So I'll make that move right here. Change to polar. And then now I can have limits for my integration. Polar coordinates, r goes from 0 to 1, theta goes from 0 to 2 pi. And then all my x squareds plus y squareds become r squareds. Unfortunate that I still have a z squared over here, but I'm not going to do the integral anyway, so I'm just going to go as far as to set it up in polar. We have the integrand is 1 minus r squared minus z squared. And then we have the square root of 4r squared plus 1. And then, since I'm changing to polar, I'm going to change this into r. dr, r goes from 0 to 1. d theta, theta goes from 0 to 2 pi. So this, I don't know if this is an easy enough integral to do. Oh, wait, I have a z in there. I can't do a z in there. What do I need to do with that z? Sorry. Oh, man, you guys taking notes in pencil? I'm sorry. I'm going to erase a bunch of things. I'm going to start back over here because when I put this down, I should have noticed that I'm dealing with a two-dimensional integral, and so I should only have two variables, and I have this third one over here. So what I need to do is I need to deal with this third one, and the fact that we're on the surface means that I need to replace any z value there with a z surface that I have. So the surface, remember, was that the paraboloid. So I need to replace that with z. So, boy. So 1 minus x squared minus y squared minus, I have x squared plus y squared minus 1 squared. Whatever this is going to be. I'm just going to leave it like that. And I was thinking about simplifying it, foiling it out, but there's 3 terms in there. So let me wrap this integral around again. Okay. Now I'll change it to polar. Now I have my integral, 1 minus r squared minus r squared minus 1 squared. Maybe that's easier to FOIL out. And then the square root of 4 r squared plus 1. And then the r, I'm going to integrate with respect to dr first. R goes from 0 to 1, and then d theta goes from 0 to 2 pi. Huh. Okay. I'd like to stop here now, and if you want to do this, you can go ahead and do it on your own. But this is a surface integral. And one application of a surface integral would be to find the mass or something like that. If you have a density function, find the mass based on this, this thing. Find the mass of a surface if your surface follows a density function formula. That's just one application. There's a bunch of other applications that the book might have. All right. So, like the the path integral, is integrating with respect to arc length, and we're integrating over a scalar function. And remember where we took the path integral? We took the path integral, and instead of integrating a scalar function, we decided, hey, we can maybe integrate a vector field in there, right? I don't know if we should do that today. No. You guys are looking. All right. Let's see if we can look at pictures. Those are my pictures, by the way. I have like the whole set of background pictures. 6, 7? I think this is 7. Oh, these are the labs. Oh, the labs are due.
When?
Today? Tonight? Tomorrow night. Yeah, we'll do a homework problem. I don't know which one either, but 16:7.
Yeah. There's one. Oh wait, this isn't the same Zara one, is it? Oh, it is.
This isn't due until like a couple of Saturdays from now, or a couple of.
No, we used to do this Sunday. Oh wait, no, the 17th is not. The 15th is not this Sunday. Oh, wait. Oh yeah, it is. The 15th is this Sunday. It's the old pictures, I think.
Oh, then here's one of your homework problems. All right, so let's evaluate the surface integral, where S is the boundary of the region enclosed by the cylinder and the planes. Oh boy, we're going to have to do. It's a crappy problem. So this is on surfaces. So when we do surfaces, we need to deal with each surface separately, it looks like. And furthermore, I think this complicates, there's some things over here that complicate our problem, in that it's a minor complication. We're going to have to parameterize with respect to y and z instead of x and y. But let's see how we can deal with that. So the boundary of the region enclosed by the cylinder. So we have a cylinder. Let's draw a cylinder. Opening up along the x-axis, right, the y and z. So y and z equal is y squared plus z squared is equal to 49. Looks like a circle of radius 7 on the yz plane, and then it's going to move along the x-axis. So I have to draw this parallel to the x-axis. Now, I have x is equal to 0 as one boundary. Maybe I should do this in a different color. And then I have x plus y is equal to 9. So x plus y is equal to 9 is x plus y equal to 9 is something like this. It's a plane. So that's going to cut this. All right, let's see if you can get your visualization on. So it's going to make a cut, and what's going to happen is that if you imagine the cylinder that goes on forever in both directions, I've already cut it at 0 in the back. So let me erase this part. So that's already been cut out. It's going to go forward a little bit at some point, and then at some point there's going to be a plane that's going to cut it. And so what it's going to leave is going to leave a kind of like an elliptical shape, where you have the surface of the cylinder, and then the back, and then the front. Can you visualize this? Can you see this? So essentially, it'll look like this. How would you describe this shape? Lipstick. Yeah, there you go.
So good. That was so smart.
This is even red. Lipstick. Perfect. All right, so this is what we want. Now, the unfortunate thing is that there's 3 surfaces involved here, and so we have to consider the 3 surfaces and parameterize all those 3 surfaces. So let's start with a S1, and I'll see if I can color coordinate here. So S1 will be the surface x is equal to 0. I should put colon here. So your surface x is equal to 0. Well, that was easy. That's all you need to do to describe the surface. But it actually has a domain. So this is x is equal to 0 is your surface, but it's restricted on the circle. This is a circle of radius 7. So it's y squared plus z squared is less than or equal to 49. So that's one surface. So the other easier surface to deal with, I think, is the top over here. We'll call this S3. S3 is this plane, x squared plus y squared is equal to 9. Now, technically, that plane, I know when I drew it, I drew an ellipse right away, but technically that plane is a whole plane. That's x squared plus y squared is equal to 9. But all we want is the intersection with the cylinder. So that's why I only drew this part. So this is the whole plane, and now when we intersect it with the cylinder, we're going to restrict using the cylinder. Y squared plus z squared is less than or equal to 49. So this is the plane itself, and this gives you the restriction. So you know what we're building here? What we're building is that we're calling this your surface S. This is somehow going to be our parameterization, and this somehow is going to be your domain or your limits. Tim? X's and Y's aren't squared. Yes, thank you. I was getting carried away with circles. You guys taking notes in pencil? All right. Now the tricky part is this cylinder. It's a cylinder. Well, cylindrical coordinates sounds like it should be a thing to use, right? So we're going to use cylindrical coordinates to describe the cylinder. Let's call this S2. And I didn't quite parameterize the first two, although the first one is going to be easy. The second one is going to be whatever. So to parameterize this one, let's jump into the parameterization. Oh boy. I'm just throwing out all kinds of nasty stuff at you. This is moving along the x-axis. So the x is going to be, I would imagine the x is going to be one of our variables. And then the other variable, if you look at this in polar coordinates, is going to be r is a radial distance, which is fixed. It's 7. So I'm not going to call that a variable or a parameter. But my theta can still be a parameter for us. And so what's going to happen is that the x is just going to be the x, and we're going to need restrictions on the x. The y is going to be, this is where you do the sine and cosine. R cosine theta, but, you know, we're going to use r is equal to 7. And then the y, and then the z is going to be the other trig function. So we're going to have a restriction on the x, because otherwise x is going to go from 0 to something. So our x value is going to go from 0, and then it goes up to and stops somewhere. Where does it stop? So look at how the x direction is moving. It goes from 0 to what? 9? Not quite. What? 9 minus y. How'd you get that? Yeah, so that it stops at that plane. It stops at the plane x plus y is equal to 9. So now you just want to replace that with an appropriate x value. So the x is 9 minus y. If you stop here at a constant number, like just 9, then you would have a cylinder that goes from 0 to 9. But you don't want it to stop at flat 9. You want it to stop at this plane, x plus y is equal to 9. So this is your parameterization for S2. So if we want to parameterize S3, let's parameterize S3. This is your x and your y, right? And we're talking about this plane. So we can imagine this thing, the shadow on the, kind of have to look at the shadow. The shadow is happening on the YZ plane, right? So I probably want my parameterization to be a YZ function. So your x is going to be, again, 9 minus y. It's the plane. The y is going to be the y, and the z is going to be the z. And then your domain is going to be this circle of radius 7 on the YZ plane. So we might want to turn that into polar, because your domain here is a circle. And in this last one, your parameterization for this one is going to be a function of YZ again. 0, Y, Z, and then the same domain, which is that circle of radius 7. So what I'm going to do between now and tomorrow is I'm going to try to see if I can draw this. I can draw this using Mathematica, but I'll see if I can draw this using graphing calculator to look at the different pieces put together with the different restrictions. And I think I'm going to need to parameterize it slightly differently, and I'll show you how that parameterization works. But we're not quite done, because we actually need to integrate this. So next time we'll pick up from here. All right?